Good afternoon, everyone. Today's lecture is about electric potential energy and how to apply the conservation of energy as well for charges in the existence of electric field, where they have both energies, electric potential energies and kinetic energy. We will also introduce and discuss the electric potential that we can calculate for any electric field. So we'll start first with refreshing our memory about the relationship between the charges. We know that opposite charges attract, like charges repel, and also the electric field points away from positive charges toward negative charges. And at the same time, the forces, if the charge that exists in the electric field is positive, then the direction of the electric field agrees with the direction of the electric force. If the charge is negative charge, then the direction of the electric field is opposite than the direction of the electric force. Also, don't forget that charges, when you release them, they tend to go toward decreasing their potential energy, exactly the same as what you have seen. When you release an object, it falls down because it tends to decrease its gravitational potential energy. So the same thing also for charges. So we've seen that the gravitational potential energy for any object is basically a function of the mass, gravity, and how far is this object from the ground. The same thing here, but this time we are dealing with charges. So the electric potential energy that's given by U, capital U here, is basically the product of the charge times the electric field times the distance from my reference. And as we'll see in the coming slides, we will be adopting different references based on the type of the electric field. So we know that in gravitational force, as we have seen in the previous lectures, if I have an object and this object is above my ground, let's say this is my reference, y equals to 0, then there's a potential energy associated with this location with respect to my reference here, such that this distance, h, for example, then I have a potential energy given as EP equals to mg, which is the gravitational force, times how far is this object from my reference. Now, as you know, for the gravitational forces, they always have the same direction. They always point toward the ground, pointing downward. So here, the direction of the force is always in the same direction, pointing downward. However, when we are talking about charges in the existence of an electric field, things are a bit different. Why? Because that depends on what kind of field do we have and what kind of a charge we also have. Is it a positive charge, negative charge? Is it an electric field that is generated from a positive plate? Is it an electric field that is generated from a plate that has negative charges? So it is different. It is not as straightforward as the gravitational potential energy. So in this case, what do we do? In this case, in order to define a correct reference, I would like you to pay attention to the way we assign the reference in case of the electric field. So I will distinguish between four cases in general. So the first two cases is when I have my plate of charges with negative charges. So those are the first two cases. I have a plate of charges such that the charges on those plates are negative charges. And then the first case is I have a positive charge Q and a negative charge minus Q. So how do we apply this expression that is U equals to Q E Y? Well, we know that the Q is the charge, and this can be positive and negative. E is the magnitude of the electric field, and Y is the distance between my reference and that charge. Now, the first two cases, if I have a plate that is negatively charged, then in this case, I will take my reference as the plate. So this is going to be my Y equals to 0. And then my positive Y is pointing in the same direction that the charge is there. So this will be my positive Y. Same thing here. If I have a negative plate, then my reference 0 is the level of the chart of the plate, and then the positive direction is pointing in the direction that I have the charge. So this is the positive Y. Why am I doing this? I'm doing this because the charge itself will move based on the interaction between its charge and the plate's charge. And I always want the sign of this electric potential energy to agree with the signs of the charge and the plate. So let's see what's going to happen. If this charge here is a positive charge, and as you can see, the plate here has negative charges, this means if I release this charge right at this location, which I'm calling here my initial location, then this charge is going to move toward decreasing its electric potential energy, which means that it will go in this direction. Why? Because it has positive charge and this is negative charge. They will attract those negative charges will attract this positive charge, and also this means that it is going toward decreasing its potential energy. So in this case, if this is my initial, let's assume that this is going to be my final destination right before it hits. So in this case, if I am to write the UI, then UI equals to, this is positive, so it's going to be Q, E, and Y is also positive. However, let's look at UF. UF will be Q, E times 0, because this is the point that it will reach right before it hits, which means I have UI greater than UF. And this is what I was expecting. This charge is going to move toward decreasing its electric potential energy. That's why the electric potential energy at this point is higher than the electric potential energy at that point. Now let's look at the second case. And the second case here, and of course, don't forget that the electric field will be also pointing in this direction. Now the second case, if I have a negative charge in the existence of a negative plate, I said that my negative plate is my reference. Then let's look what's going to happen. If this is my initial location, and as you can see here, since this is a negative charge, and this plate is a negative, this plate has negative charges, then this pointed charge will move toward decreasing its potential energy, which means due to the repulsive force here, this is charge. If when I release it, it will go in this direction. So if it goes in this direction, so then let's assume that this point, for example, will continue. Let's assume that this point is in its way going toward decreasing its potential energy. I want to evaluate the electric potential energy at I and at F. So in this case, again, this is my reference. So this one is Y1 or YI. And this point is YF. Then if I am to write UI is minus Q, because it's negative, EYI, and UF is minus Q, EUF. Now, YF, yes, indeed, is greater than YI. However, because of the minus, UI is greater than UF. So indeed, the electric potential energy at I, at the point I, is greater than the electric potential energy at the point F. Although YF is greater than YI, but because of the minus, YUI is greater than UF. Now let's look at the other two cases. The other two cases, I have the plates as charged with positive charges. And I have a positive charge here, positive Q, and I have a negative charge here, negative minus Q. So in this case, I will take my reference as the charge, and I will point the positive toward the plate. So this one is Y equals to 0, and this one is positive Y. Same thing here. This is my reference, Y equals 0, and then pointing toward the plate. So in this case, if I am to write, this is my point, the initial point. If I release this positive charge at this location, then this positive charge is going to go in this direction. So let me assume that this point is my final destination point. Then in this case, if I am to write UI, which is QEY, in this case, UI, because it is at the reference, will be 0. However, UF is QEY, and in this case, UF will be, this is my reference, I will be reading a negative value here, then this is going to be a negative value. So definitely UI is greater than UF. Now here, same thing. Don't forget now that the electric field is pointing in this direction. Now here, if I calculate UI, this is my I, and this is, in this case, because it's negative, it will go in this direction. So now this is my my F. So UI is minus Q E Y, and then since it's at the reference, then UI is 0. However, UF at this point will be positive. Then you call this one from here to here as YF. Then UF as minus QEYF, and this is also a negative number, then UI is greater than UF. So in all cases, when I release a charge, it will go toward decreasing its electric potential energy. So this is how we do the referencing for the negative plates and for the positive plates. Okay, so now we know how to put the reference, put the positive direction based on the electric field that I have, based on what plate I am doing the calculation with respect to. Now let's move on to this example. Here in this example, we have a proton, which is positive charge located in a uniform electric field of a magnitude 150 Newton per Coulomb. We need to, if the proton is 1 meter from the plate, so this is 1 meter, we need to calculate what is the electric potential energy relative to the plate. What direction will the proton move if it's released? Does the electric potential energy increase or decrease once it's released? So let's start first with the first part A. So we have a negatively charged plate. We know how to put the reference for a negatively charged plate. So my 0 would be here, and then my positive is toward the direction of the charge. And I have here a proton, Q, positive. The electric field is 150 Newton per Coulomb. We have the distance here. We call this one Y as 1 meter from the plate. We need to calculate. So we have here the charge as 1.602 10 to the power minus 19 Coulomb. We need to calculate the electric potential energy relative to the plate. So in this case, I have U equals to Q E Y, and U here in this case is 1.602 10 to the power minus 19 times 150 times 1 meter, and the electric potential energy becomes 2.4 10 to the power minus 17 joules. Okay, so now the potential energy here, just for the sake of understanding, since we have taken this reference as 0, then definitely my electric potential energy at this point is assumed to be 0. Now the next part is what direction will the proton move if it's released? Definitely it will move toward decreasing its electric potential energy, and in this case this proton is going to go in this direction. Yes, it is decreasing its electric potential energy. So move to the next slide. Here we have an electron that is located at 1 meter. So everything is the same except it is an electron, same electric field. So let's see how this is going to change. Now, if that's an electron, here we were having the plate charged with the same charges, so this is negative. Again, since this is a negative plate, I will take my reference here, 0. I have my electron here, so here now the charge is minus 1.602, 10 to the power minus 19 Coulomb. The positive is pointing up this way, so this is my charge. Now I need to calculate the electric potential energy relative to the plate. So U in this case is a Q E Y. So Y is 1 meter. 1 meter. So here I have U is minus 1.602, 10 to the power minus 19 times 150 times 1, and the electric potential energy in this case becomes minus 2.4, 10 to the power minus 17 joules. Again, this is my reference, so definitely the electric potential energy right here at my reference is 0. And this electron now it will move in this direction toward decreasing its electric potential energy. So we have here 0 and then negative, and then it will become more negative, which means its electric potential energy is decreasing. Now for this example, we have for a problem involving electric potential energy, setting up the y equals to 0 position and the positive y direction is important to getting the signs right for the configuration below, involving a proton and the uniform field created by a positively charged plate. Which of the following setups is the best approach? So for the case of the positively charged plate, we know that the location of the charge should be my reference 0. So in this case, it will be either this or this. Both of them, they have the reference 0 at the charge. So this is wrong, this is wrong. However, the positive y will be pointing toward the plate, which is in this case, it will be A. So A is correct. So we will choose A based on the configuration that we talked about earlier. Now, the conservation of energy in our electric potential energy is the same as what we have seen earlier. What we have is the electric potential energy plus the kinetic energy at any point equals to the electric potential energy plus the kinetic energy at the second point. So in this case, if I am to move y1 to this side and move ek2 to that side, in this case, what I'm getting is u2 minus u1 equals to ek1 minus ek2. If I rearrange such that I start with ek2, then it will be u2 minus u1 equals to minus ek2 minus ek1, and this one is called delta ek, and this one is called delta u. So for the conservation of energy, I didn't change anything. I only rearranged such that on one side I have the electric potential energy, and on the other side I have the electric potential energy. So I have here delta U equals to minus delta EK. So this is the conservation of energy that we have seen earlier. It is the same. We will be applying it on on the electric charges. Okay, so what do we have here? We have an example with the conservation of energy. So let's look at this question here, trying to apply the conservation of energy to solve it. We have an electron starts from rest. So this electron is starting from rest, which means that the velocity here is 0. This electron is 5.2 centimeters from positively charged plate. The plate creates uniform electric field. We're assuming that we're very close to it, in the region with a magnitude of 220 newtons per coulomb. What is the electron's speed just before it hits the plate? We have the mass of the electron as 9.11 10 to the power minus 31 kilograms. So let's solve this problem. So here, what do we have? We have a positively charged plate. So it is very important to know what kind of charges I have in order to apply the same orientation that we talked about. So here we have an electron. Electron Q is minus 1.602 10 to the power minus 19 coulomb. And I have the electron here. In this case, this electron, the location of this electron will be my reference, y equals to 0. And my positive will be pointing toward the plate. So this is my plus y, right? So if I am to apply the conservation of energy, first of all, I need to identify the distances and the speeds. So I know this is 0.1, and this is right before this electron hits the plate is 0.2. So in this case, I have delta U equals to minus delta UK, which means I have U2 minus U1 equals to minus EK2 minus EK1. So if this electron is starting from rest, I have V1 equals to 0, which means the kinetic energy is 0. EK1 here is 0. I want EK2, so I know that this is minus half m V2 squared. Y2. Y2 here becomes Q E Y2. However, Y1, because it is at my reference, it will be 0. Now, don't forget that this one is negative, then I have 0.602 10 to the power minus 19 times 220 times 5.2 10 to the power minus 2 equals to minus half times 9.1 10 to the power minus 31 times V2 squared. So if you rearrange the equation and solve for V2, then V2 becomes 2.010 to the power 6 meter per second. There is an alternative solution to solve for this problem. In this alternative solution, we can use the forces and the acceleration and the 1D kinematics by calculating the acceleration. We know that F equals to QE, and also I know that F equals to MA. So equating those two forces, right? I know that A, the acceleration is QE over M. So if I know get the acceleration, I know the distance, which was 5.2 centimeter here. Delta y is 5.2 centimeter, which is 0.052. I found the acceleration, and it is going based on my reference. Acceleration is positive. Delta is positive. Starting from rest, I can calculate the velocity right before it hits the plate. Now let's move to the electric potential. Basically, the electric potential is a parameter related to the electric field itself, such that at specific points in the existence of an electric field, there is an electric potential related to that location. If I bring a charge and put it in this location, then this charge will have an electric potential energy, such that this electric potential energy U equals to Q times the electric potential. We know that the electric potential is given as joules per Coulomb, and this is also the unit of 1 volt. So as I said, the electric potential energy that equals to QEY, and the electric potential is related to the charge. So in this case, if I am to move Q to the other side, I get U divided by Q equals to EY, and this is the electric potential. And as you can see, this electric potential is related to the electric field. The distribution of the space within an electric field basically will have unique electric potential values. So if I bring a charge and put it in this location, then that charge will have an electric potential energy U equals to Q times V. As I said before, the electric potential is related to the electric field. Those space within this electric field, they have every point in that region has a unique electric potential. So it is related to the electric field. However, the electric potential energy is associated with the charge in that specific location that has an electric potential. So it is related to the interaction between the charge and the electric field, the electric potential energy. Last example here for this lecture is we have two plates. One of them is positive, the other one is negative, with a potential difference of 6 volts between the negative and the positive, with a distance of 1.1 centimeter. The electric potential difference is 6 volt, as we saw here. What is the electric field between the plates? What is the electric field between the plates? So in this case, we redraw. We have the positive, negative. V here is 0, V here is 6 volts. Distance is 1.1 centimeter. We need, what is the electric field? The electric field, as we have seen, V is V Y, and V now here is the difference between the positive and the negative. So we have 6 equals to V times 1.1 10 to the power minus 2. Then the electric field is 545 Newton per Coulomb. And the electric field is pointing from the positive toward the negative. So this is the electric field pointing in this direction. Part B, if a proton starts from rest at the positive plate, so we have here a proton at the positive plate, start from rest, what is its speed when it's halfway across the region? So right here, halfway across the region, so we have here V1 equals to 0. We need V2 right here at a distance of 0.0055 meter, which is half. So if I am to look at this as my reference here, this is my y equals to 0, and then I will be pointing toward the positive plate, so this is my plus y, right? Then in this case, I have here, applying the conservation of energy, I have U2 minus U1 equals to minus EK2 minus EK1. So the reference is at V1 equals to 0, which means I have here, this is my reference, that charge, which means U2 as, how much is U2? U2, that's a proton going in the negative direction, so this one becomes a Q E Y2. U1 here is 0 equals to minus, also EK1 is 0, half mv2 squared minus 0. So Q here is 1.602 10 to the power minus 19. Electric field is 545 times Y2. Y2 here is a negative distance. This is minus 0.0055 equals to minus half proton is 1.67 10 to the power minus 27 times V2 squared. Minus will cancel with the minus, and in this case, V2 is 2.4 10 to the power 4 meter per second.